All right, in 8.7, we're going to be talking about something called the power of a test, and it's the power of a hypothesis. The power of a test against a test is the probability that the test will reject the null at a chosen significance level alpha when the alternative is true. So, in layman's terms, what does that mean? That it's the probability of correctly rejecting the null. Why would we correctly reject it? Well, we would correctly reject it if the alternative is true. So that's what power is. It's the probability of correctly rejecting the null. Will you be expected to calculate the power of a test on an exam? No, you will not. You just need to be able to interpret it and tell me ways to increase power. So that's what we have here. There's 3 ways to increase power, and I'll illustrate these in some examples in a minute. But go ahead and write these down. 3 ways to increase the power is to increase the sample size, increase the significance level, and thirdly, increase the effect size, which I'll show you what that is as we go. So the best way to model this is for you is through examples. So here's the scenario. A potato chip producer is the main supplier, and its main supplier agree that each shipment of the potatoes must meet certain quality standards. If the producer determines that more than 8% of the potatoes in a shipment have blemishes, the truck will be sent away and to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make the potato chips. To make the decision, the supervisor will inspect a random sample of potatoes from the shipment. The producer will then perform a significance test using the hypothesis. Suppose that the true proportion of blemished potatoes is 10%, or 0.10. This means that we should reject because the proportion is greater than 8%. All right? That's in theory. So A says, will the inspector be more likely to find convincing evidence that that proportion is greater than 8% if he looks at a small sample or if he looks at a larger sample of potatoes? And how does the sample size affect power? Well, as we've seen in other things, the larger the sample, the better the representation of the population. So it gives us better evidence of what's really going on. It gives us a better chance of making a good decision. So a larger sample is what we want because it gives more data, gives a better chance of making a correct. Okay, larger sample, more power. So greater the sample size, the greater the power. Okay, now same scenario with potato chips. Can't have a shipment that's more than 8% blemished, right? So B says, will the inspector be more likely to find a convincing evidence that the proportion is greater than 8% if he uses an alpha level of 0.10 or 0.01? How does the significance level affect the power? So what you have to keep in mind is, let's say it's a greater than test, so it's going to be a right tail test, right? So what I'm drawing here is if alpha is 0.10. So if you look at this area of the curve, there it is. Now, versus if I draw a curve where alpha is 0.01. That's much smaller. 1% is much smaller than 10%, right? Terrible curve, but you get the idea. 1% would be this teeny tiny little bit of the tail. So thinking about these two great drawings, okay, look at the area of the curve. Which one's going to be easier to reject, find evidence to reject? One that has a bigger area, a larger probability space, or a smaller one, okay? There's a lot of probabilities that can fall within this, right? 0.1, 0.9, 0.8, 0.7, 0.6, all the way down, right? And in this, there's really just 0.01 and 0.000, but teeny tiny probabilities can fall in this space because it's just a smaller area under the curve. So which one are you more likely to be able to reject the null with? Well, you're more likely to reject if the area is big than if the area is small. Okay? So which is he more likely to find convincing evidence of that? Well, he's more likely to find the evidence if alpha is the 10%, because it will be easier to reject the null with a larger area, or you could call it a larger rejection region. Be easier to reject the null with a larger rejection region, which means, therefore, less likely to make a type 2 error. Okay, so sum it up. If we increase our alpha, we increase our power. Okay, and alpha is really the rejection region. If we make that region bigger, there's more to reject. If we keep it smaller, we're less likely to reject. It's that simple. All right, same thing, potato chip scenario, can't be greater than 8% blemished. So let's look at this. Suppose that a second shipment of potatoes arrives, and the proportion of blemished potatoes is 0.5. Will the inspector be more likely to find convincing evidence that the probability is greater than 0.8 for the first shipment, which was 0.10, or for the shipment of 0.5? And how does effect size affect power? Okay, so what we look at is, all right, look at what's in our null hypothesis. It's the 0.8, right? 8% is our money number. So we look at the effect size. So let me define that for you. Effect size is the difference between the hypothesized value and the truth. Truth being the true proportion that we know we have. So effect size is the difference between the hypothesized value, in this case, which is the 0.8, and the truth, which is the proportion. So our first one has the truth of 50%. So it's the difference between 8% versus 50%, or 8% versus what's the other shipment had a true percentage of 10%. Well, which one's going to be more noticeable? Okay, which has the bigger difference? Well, 50% from 8% is a huge difference, right? 42%. 8 to 10 is only a 2% difference. So which one's going to be easier to detect? Well, the one that's at 50%, okay? Because it's much further away from the hypothesized value. So we could say this. It's easier to detect the shipment bad when the actual proportion of potatoes is further from the hypothesized value. Okay, hopefully that's putting it in words. You know, the distance between 8% and 50% is much bigger than 8% and 10%. That's the effect size here. Okay, so D just says, is there anything else that could affect your power? Yes, some things could, like controlling other sources of variability. Controlling other sources of variability makes sample more accurate. And if it's more accurate, there's more power. Okay, so effect size increases, then your power increases. And then this just other little piece that could affect power is just making sure you control variability, like stratify your sample or something that makes sense in this scenario. All right, so in part E, it says, suppose that the true proportion of blemished potatoes is 11%. If alpha is 0.05, the power of the test is 0.75. And this says to interpret the value. So this is how we would interpret the power. Okay? Remember, the power is the probability of correctly rejecting the null if the proportion is what they gave us, right? So we would say, if the true proportion of blemished potatoes is P equals 0.11, then there is a 0.76 probability that the supervisor will find convincing evidence that, and then you restate the alternative, that the probability is greater than 0.08. Okay? So we refer back to the proportion they gave us. If the true proportion of blemished potatoes is 11%, there's a 0.76 probability that the supervisor is going to find convincing evidence that the proportion is greater than 8%. Right? Now, let's look at these same fake beings in another scenario, real-life example. So, when the accounting firm AJL and Associates audits a company's financial records for fraud, they often use a test based on Benford's law. Benford's law states that when the distribution of the first 3 digits in many real-life sources of data is not uniform. In fact, when there's no fraud, only about 30.1% of the numbers in financial records begin with the digit 1. However, if the proportion of first digits that are 1 is significantly different from 0.301 in a random sample of records, then this company does a much more thorough investigation, or audit, basically. Suppose that a random sample of 300 expenses from a company's financial records results in only 68 expenses that begin with the digit of 1. We tested the claim at 30.1% of the numbers in the financial records begin with the digit. So suppose that this proportion is 25%. That is 25% of all financial records of this company begin with the digit 1. When alpha is 0.05, the power of the test is 0.58. So interpret this value. Okay? So if we interpret it, we would say if the true proportion of records that begin with a 1, digit 1, is 0.25, then there is a 0.58 probability that the AJL associate will find convincing evidence for, what does my alternative say? That the probability is not equal to 0.301. Okay? So we know it's not equal because it says significantly different from. All right? So that's how we would interpret power. Look at the next question, same scenario. B says, how can the associates increase the power of their test? Well, we've talked about several ways. They can increase the significance level. Okay. The downside to that, let's think about this. It's more money, more time always. But they might actually call for an audit when they really didn't need to. So let's say that they're more likely needlessly investigate. Okay, so if you increase your significance level, you might end up investigating something that didn't need to be done. Another way they could increase their power is to increase their sample size. Downside to that, that's more time and money, right? Third way they could do that is effect size, but really they don't have a lot of control over that. But they could make sure they used a stratified sample. And again, a downside of sampling so strategically could be time and money. Now, I know this question didn't ask you for the downside, but I want you to always think of it that way. All right, lastly, for what values of P would the power of the test be greater than 0.58, sorry, assuming everything else stayed the same. So let's think about what the power is right now. Right now our sample is 0.25, right? And the null value is 0.301. So we look at what's the difference between 0.25 and 0.301, and if I look at the difference here, this is 0.051, so if I add 0.051 to 0.301, I get 0.352. Okay, so it's saying this has the same power, right? If I found a sample here and I found a sample here. So it's trying to increase the power by increasing this distance right in here. Okay, we want to increase this change. So how would I describe that? Well, I would say that any value where P is less than 0.25 or greater than, P is greater than 0.352 would increase the power. Because what have we done? We've increased the effect size. Okay? So I hope that makes some sense to you, and we will talk through these again when we get to class so that you have a good understanding of the 3 ways we can increase power and how do you interpret power correctly.